we defined a product. So let us take this. So this was what we have been doing in our product. So let us take that V over F be a vector space where F is R or C, and we defined a mapping here from V cross V to F, such that this UV going to the image is denoted by this type of bracket, such that, so if I have to rewrite, then and this becomes, let us take that this U comma U is greater or equal to 0, and U comma U is 0 if and only if U is 0. Yes. And number 2, the complex number U comma V, if you take the conjugate, is same as V comma U. And number 3, alpha U plus beta V W is same as alpha U W plus beta V W. That means it's linear in the first coordinate. For all alpha beta in F, and for all U, V, W in V. Okay. And using these properties, so we also obtained that in the second coordinate, this also can be seen using this second and third. So we can use that U alpha V plus beta W as alpha bar, and this is U comma V plus beta bar. This is U comma W. So this is a simple conclusion from second and third that one can have. So this is what we have done, and then we had some examples. We also had seen that one important inequality that we proved, known as the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is, to recall once again, that so it's Cauchy-Schwarz inequality. So so for an inner product space, so in an inner product space, V over F. The Cauchy-Schwarz inequality says that the modulus of the complex number, the inner product of U with V, is less or equal to the product of the norms of the vectors U and V for all U, V, and V. So this is what we had done for this. Recall the norm of a vector was denoted by, so where the norm is actually the positive square root of U comma U. That's how we. And using this, we also can obtain the properties of the norm. So a norm is a non-negative real number, and it's 0 if and only if U is 0. And norm of alpha U is, let me state, is called the norm. is called norm of U. So norm of a vector U in V over F we have defined as the norm of U, the positive square root of U comma. And it has the properties. So the properties of the norm. So you can see that the norm of U is a non-negative real number, and this norm of U is 0 if and only if U is 0. Number 2, you can see that the norm of alpha U is same as modulus alpha norm U. Because alpha is a complex number, so this is the modulus to denote for this one. Third thing is that what we have proved, Cauchy-Schwarz inequality, that also can be treated as one of the properties. Cauchy-Schwarz inequality. So what is this Cauchy-Schwarz inequality? The modulus of the inner product less or equal to the product of the norms of vectors. Can also deduce as such from here. So some applications of the Cauchy-Schwarz inequality, you can also use these to prove what is called the triangle inequality. The triangle inequality. So to prove the triangle inequality says that norm of U plus V is less or equal to norm U plus norm of V. Now, the first three we have already proved. Now, for the proof of the fourth so this is for all alpha in F and for all UV in like inner product space with V over F. So for this, observe the following, that so the norm of the U plus V square has it been defined as the inner product of U plus V with U plus V. And using this linearity here, because there is no scalar multiples are involved, so you can treat that this is linear in both the coordinates. So this is U comma U plus U comma V plus V comma U plus V comma. So this is the inner product spaces. Recall that the first one is the norm of U square, and the last is the norm of V square. Now here you have plus this is U comma V, and this is the conjugate of V comma V. So V comma U is the conjugate of U comma V. So this is the conjugate of this. So it's the conjugate of this. So this is Z plus Z bar. Now Z plus Z bar, so when you say, so that becomes real. If Z is X plus iota Y, then Z bar is X minus iota Y, and Z plus Z bar will be twice of X. So this term second and third, because this is Z plus Z bar, where Z is U comma V, is twice of the real part of Z. So that means twice the real part of U comma V. So what we have got so far is as follows. So this is a norm of U plus V square is equal to norm of U square plus twice the real part of the inner product u with v plus norm of v square. Good. Now, you can also see easily that this can be written as norm of u square plus norm of v square plus twice the real part of u comma v. You can observe that for any so you can see that if z is x plus iota y and z bar therefore is x minus iota y. So z plus z bar, this is twice of x, which is the twice of the real part of z, which is x. So this you can see that x is always less or equal to the square root of x square plus y square. Equality will occur. Equality will occur when you have this y0. And if you are taking this x as the positive number, so modulus of x, you can say that this is always less or equal to. So modulus of x is always less or equal to the square root of x square plus y square. So this is what it is. And so x as well as minus x both will be less than that. So this means that x is less or equal to x square plus y square. So the real part of z, the real part of z is less or equal to this modulus here, x plus iota y. This is what it is. And in our context for z is equal to this inner product uv. So this real part of the inner product, this is less or equal to. So this is the modulus of the inner product. Modulus of the inner product. So this is this. Now this is twice, so this will be twice of that. So this, therefore, because of this, is less or equal to norm u square plus norm of v square plus twice. So here this will give you that this is less. This is your modulus now will be, because this using the Cauchy, the modulus of this. So this real part of this uv, this is less than modulus of this, and which if you apply the so this means that this is a further real part of this uv less or equal to, in the Cauchy-Schwarz inequality will say that this is less or equal to norm u norm of v. So if it is twice, then this is less or equal to twice of this norm. You can see that this is a square plus b square plus 2ab, and this is actually norm u plus norm v whole square. Now taking the positive square root here, so norm of u plus v is less or equal to norm u plus norm v. So this is for all u, v in the vector space Vf, which is an inner product space. So as an application, what we have got is the triangle inequality. So what is the triangle inequality? Triangle inequality is that for any two vectors u and v, norm of u plus v is less or equal to norm u plus norm v. There is another, there are many applications of such. So you can see this is fifth, for example. And the fifth is called the law of parallelogram. So Law of parallelogram or parallelogram law. The law of parallelogram. So what does it say is, of course, if you draw in the plane a parallelogram, so it says that the sum of the diagonals is less or equal to the sum of the sides. And if you generalize this in case of, say, an arbitrary inner product space, this will be translated into saying that the norm of u plus v square plus norm of this u minus v square is the sum here of the sides. The sides represented by the vectors, let us say u and v. So this is what it says. Law of the parallelogram. U plus v and u minus v naturally will denote the diagonals. So to do this, you again will have to, so this I leave for you. It's a simple thing that we have done just now. So you will write for you norm of u plus v as well square as well as norm of u minus v square, and then you can use that. So norm of u plus v square is the inner product of u, or hint you can see that norm of u plus v square is u plus v with u plus v. And just now, if you see what we have done is, so this is u plus u v plus v u plus v v. And if you replace v by minus v throughout, then this also give you that norm of u minus v square is, so u will stay as such wherever this is u, and this is minus v plus minus v u, and this is minus v minus v. So this second one is that u plus, so this is minus v, so it will come out. So this will be minus of this. So this will be minus of u comma v. And this is also minus of v comma u. And this once minus comes, then again minus comes. So this will be plus v comma v. Now you can see if you add the two, so u plus v norm square plus norm of u minus v square. Now you can see that there are terms which are common and with opposite signs. So u comma v here with positive sign, u comma v here is with negative sign. So these two cancel with each other. The same thing happens with v comma u. So in the first it is with positive sign, in the second it is with the negative sign. So what stay is that u comma u and v comma v, and they are repeated, so they are twice. So twice of this, twice of this u comma u plus twice of v comma v, and u comma u is the norm of u square, and 2 you can take common, so this is norm of v square. So this is called the law of parallelogram, that for all uv in the inner product space we know as. So this is also an important property in an inner product space. Of course, what we do in the schools is when this v is r2 over r, and you get that this are the diagonals. Sum of the squares of the diagonals is equal to the sum of the squares of the sides of the parallelogram. All right, so let us have one more interesting property. You can also prove the same. There are many interesting properties, of course. let us take this is the sixth. So sixth in a product space. So if you take V to be Fn, if Fn over F, then with respect to the standard inner product, with respect to the inner product defined by say U comma V for say U as say x1, x2, and say xn, and V say y1, y2, yn. Yeah. Okay. So if you take, for example, Rn over R, say you take Rn R. First, this data with this. And the inner product is defined as xi,yi. So x1y1 plus x2y2 plus n x and yn. These are real numbers. So xi, yj's are real numbers. Okay. What the Cauchy-Schwarz inequality will tell us. So by the Cauchy-Schwarz inequality tells us is that mod of this inner product U comma V is less or equal to norm U norm V. So if you substitute here, what you will see that this is the modulus here. So this will imply that now in this case Rn over R. So these are the complex numbers. So this is the modulus of the inner product. Inner product is this x1y1 plus x2y2 x and yn is less or equal to norm of U. Norm of U, U with U. U with U means the square root of. So this is x1 square plus x2 square plus xn square times norm of V. So what is norm of V? Is y1 square plus y2 square yn square. And this is what it is. So the square root of this. So modulus of this will be you can generalize this if V is Cn over C. In that case, what will be the case? So Cn over C. And the inner product for with respect to the inner product. So if U is say Z1, Z2, Z1, Z2, and let's say Zn, and V is Z1 prime plus Z prime. So what we know is that Zi and Zi prime are complex numbers. In that case, this will give us, if you take the inner product here, U comma V, as, so this is Z1 prime, and Z1 prime's conjugate. So this is Z2 prime conjugate. You can take that this is Z1 prime and Z1 conjugate is also the same thing. So Zn and Zn prime conjugate. So if you take this, then this is an inner product that we know. And if you apply the Cauchy-Schwarz inequality, that means modulus of the inner product here. So modulus of this, so Z1 prime plus Z2. And this is the bar, Z2 bar. So this is plus Zn prime bar modulus is less or equal to. So it's norm of this. Norm of this here will be the square root here. So mod Z1 square plus mod Zn square times modulus of this V. So norm of V. So this is Z1 and this is prime square plus Zn prime square. So this is what is called now Cauchy-Schwarz inequalities application to the complex inner product space Cn over C. There are many other interesting properties. For example, if you take V as the set of all continuous functions which are complex valued and are defined on a closed interval 0, 1, say FTGT. So T varies 0 to 1 as a real number. You can define the map from V cross V to F. F is a complex number. Say FTGT as integral 0 to 1 FTGT bar dt. You can check that this is an inner product. And if you apply the Cauchy-Schwarz inequality, this will give a very important observation that the modulus of the integral is less or equal to the product of the integrals of the modulus square. So eighth. So this is the eighth. So if you take if V to to be the set of all continuous functions. So say this is f from 0 to 1 to the complex numbers c. So this is t here, and what you get is ft. Ft is a complex number for every t. And they are continuous. So that f is continuous. You can check that this V over F is an vector space and is an inner product space. So V over F is an inner product space with respect to the inner product defined as follows. So F with G. So Ft Gt integral 0 to 1 Ft Gt. Now this is a complex number, so this bar also makes sense, dt. And by Cauchy-Schwarz inequality, this by Cauchy-Schwarz inequality, what we get is here that the modulus of the inner product, so that means Ft Gt is less or equal to. So instead of taking square roots, so let me take squares on both sides. So this is less or equal to 0 to 1. Modulus Ft square dt times 0 to 1 gt modulus square dt, the product of these two integrals. So like that, there are many interesting properties. One more, if you want, you can also write as the Bessel's inequality also. So the Bessel's inequality can be written as, so this is for you, and ninth, so that also you can prove. But for ninth, you will need what is called normality. So the Bessel's inequality. Bessel's inequality. So what it says is that if say W1, W2, and say Wm in V over F and inner product space is an orthonormal set. An orthonormal set. Then what should happen? That the summation of this Wi V, the inner product, squares I1 to M is less or equal to norm of V square. That happens for every V in V. So there is a term here what is called orthonormal set. So we defined what is orthonormal means. So like that, there are many interesting properties. So for ninth, you will need what is called orthonormal. So before that, we needed to define this orthogonal set. Orthogonal means two vectors are said to be orthogonal if they are perpendicular. And here, perpendicular, so if you remember in R2, that was equivalent to saying that the angle between them is pi by 2, and that leads to equivalently that the dot product is 0. So taking Q from there, so what we define two vectors to be orthogonal if their inner product is 0. And we say orthonormal if the vectors are orthogonal as well as the norm is 1. All right, so orthogonality. Orthogonal. So let us say V over F be an inner product space. So two vectors, let us say V1 and V2 in V over F are said to be, or V1 is said to be orthogonal to V2. You can check that if V1 is orthogonal to V2, then V2 is orthogonal to V1. And therefore, we can say that they are orthogonal to each other. So orthogonal if the inner product V1 with V2, which is same as, of course, V2 with V1, this is same as this, is 0. And orthonormal set means if it consists of orthogonal vectors with norm 1. So orthogonal set means, so a set of vectors say V1, V2, and say Vn in V over F is said to be orthogonal set. Orthogonal set if Vi and Vj are orthogonal to each other for I different from j. Orthonormal means, so an orthogonal set let us say V1, V2, Vn in V over F is said to be an orthonormal set if, in addition to there being orthogonal mutually, norm of each Vi is equal to 1. So suppose there are two vectors V1, V2. V1, V2 orthogonal, and norm V1 is 1, norm V2 is 1. Then the set consisting of V1 and V2 is said to be an orthonormal set, exactly these two elements. Now, this is also interesting that we want to see about the orthogonal things, a few things. So let us take V over F be an inner product space. So F is R over C. F is either R or is C, complex numbers. And W be a subspace of V. Then W is also an inner product space, naturally, with respect to the inner product of V. And if you consider this set, this W perpendicular or W orthogonal, of all vectors, say V in V, which are orthogonal to every vector of W. So this consists of vectors in V. So this is subset here. So this is subset of V over F. In fact, you can check that this is a subspace. So this, I change the symbol therefore for subspace. So you can check that this is a subspace of V. So what do you do for that? You just check that this is closed with respect to addition and is closed with respect to the scalar multiplication, which is not a difficult thing. Now this is a subspace here. So we have two subspaces. One is W, and corresponding to W, we have W orthogonal. What we intend to prove is this theorem, maybe tomorrow, that for the inner product space V over F, W and W orthogonal, they sum to V. So V is direct sum of orthogonal. And for this reason, this W orthogonal is called complement. So this is called orthogonal complement. And hence W this is called, also called orthogonal complement. Called the orthogonal complement of W in U. Now for this, one thing is straight, because we need to prove two things, that this is sum and the intersection is 0. So we need to prove for this two things. One is that this is sum, and another thing that we need to prove is that their intersection is just 0. Now this second one is rather straightforward. You can check that if you have a vector which is in W as well as in W orthogonal, so for second, if W is in W intersection W orthogonal, then W must be orthogonal to itself also, because this is orthogonal. Any element in W orthogonal is orthogonal to every vector in W, and in particular with W also. This is norm of W square, and this is 0. If 0 means what you get is, so this is if and only if W is 0. So what we have is that the intersection is 0. So what remains is to prove is number 1. Number 1 means that it can be written as the sum of W and W orthogonal. This theorem is so important that its various proofs are available. We also would like to do 1 or 2 proofs depending on time. So let us have just some simple observations and about the orthogonal set or also normal sets. So let us have this. First thing is that you can prove that the orthogonal vectors are linearly independent. We shall prove this theorem. So for 1, we should need a few results. So first is this theorem that we want to prove, that an orthonormal set if we have, then these vectors are linearly independent. So the vectors in an orthonormal set in an inner product space are linearly independent. The vectors in an orthogonal and therefore for orthonormal also. Orthogonal set of an inner product space are linearly independent. So for the proof, what we observe is as follows. So let us say that S be, no, this may be finite or infinite. So let us take this S finite or infinite, or infinite. Be a set of vectors, be a set of vectors which are orthogonal, and let us take which are non-zero, which are non-zero and orthogonal, and mutually orthogonal. So let us take V1, V2, let's say Vn, Vn, S. So what we know that each of them is non-zero, and they are orthogonal. That means so then each Vi is non-zero, and Vi, Vj is 0 for every I other than J. This is what it is. All right. Now let us take W to be this. Say alpha 1 V1, alpha 2 V2, alpha n Vn. Now this naturally is a linear combination, and therefore this is here in F. This is your F. Is in the linear span of S. And observe that if you take the inner product of W with Vk, that means what? This is the inner product alpha 1 V1, alpha 2 V2, alpha, and say here n Vn and Vk. K is of course 1 to n, but these are these. Now this because of the linearity in the first coordinate, this will be same as, so alpha 1 V1 K Vk plus alpha 2 V2 Vk alpha n Vn. Now what you can see is that because they are mutually orthogonal, so when k is different from I, for each I, Vi, Vk will be 0. Otherwise, this will be Vk, Vk. So only one term will constitute here because k is fixed. So this will be alpha k, Vk, Vk. And this is same as alpha k, norm of Vk square. And now this is, now Vk is not 0. So norm of Vk is not 0. The norm of Vk square is also not 0. So this is what it is. Now, since Vk is not 0, norm of Vk is not 0, and therefore its square is also not 0, and it's a real number, so you can divide therefore by norm of Vk square. So what we get therefore is from here that this will be alpha k as inner product WVK divided by norm of Vk square. So what we have got here is that alpha k is inner product W with Vk divided by norm of Vk square, and this happens for every k 1 to n. Okay. Now if the linear combination is 0, what we want to prove? That alpha IVI linear combination is 0, then each alpha must be 0 so that they are linearly independent. So this linear combination is this alpha IVI I1 to n is 0. Then what will happen? This will imply that alpha k, the coefficients which are inner product this with Vk, by norm of Vk square is 0. And that is for every k 1 to n. Now norm Vk square is not 0. So this division is permitted. So each coefficient is 0. So that makes that V1, V2, Vn are linearly independent over F. That's what we wanted to prove. So as a corollary from here, what we can write here. So as a corollary, what we can write here. So if a vector, let us say W in V, is a linear combination of a sequence of orthogonal vectors of a sequence of orthogonal vectors, say V1, V2, and so on, Vn in V, inner product space Vn, V over F, then this W can be determined as the W. So if the linear combination is alpha AVI, so these alpha i's can be determined in terms of this, and therefore replacing this. So alpha k will be WVK by norm of Vk square. This is the scalar, and Vk, this is the linear combination, k is equal to 1 to n. So this is what is alpha k Vk. Alpha k, k, k1 to n. Where what is alpha k? Here alpha k is k binormal k square for every k. And so we can write like this as a linear combination. So we shall wind up here. Thank you very much for your kind attention. And we shall take up from here to prove the main theorem.
Thank you, sir.